Hi, this is my 125th video on Financial Math for Actuarial Exam 2. Yesterday I made a couple videos and it was a snowy day. Today, as you can see, it's bright and sunny here at Bethel University in St. Paul, Minnesota, which means in January it's usually very cold, and yes, it's below zero today. Very cold day, but again, I'm nice and toasty warm inside here. We're going to go back to Broverman's book in this video, Mathematics of Investment and Credit, 6th edition. Problem 5.1.4. It's going to be kind of a long video because we're going to introduce some terminology, notation, and some new ideas, really. We're going to be comparing net present values of two cash flows at different interest preference rates. Okay? It's a pretty important subject here, so I think it'll be worth your while. So we're going to be comparing two transactions. Transactions A and B are to be compared. That's the overall goal. Transaction A has the following net cash flows. At time 0, it's -5. At time 1, it's 3.72. At time 2, it's 0. And at time 3, it's 4. Transaction B has net cash flows at time 0 of -5, time 1 of 3, time 2, it's 1.7, and at time 3, it's 3. Part A is something we've done before. Find the internal rate of return, IRR, or yield rate. And in fact, in Broverman's book, in this problem, it just says yield rate, but I put IRR in parentheses there. For each transaction to at least 6 decimal places, we'll just use the financial functions on the calculator for that. Part B, this is something new. Show that transaction A is preferable to B at a certain range of interest preference rates, less than 11.11% and greater than 25%. And on the flip side, B is preferable at interest preference rates between 11.11% and 25%. So new idea here, interest preference rate. And to help us think about this, also another new idea is going to be net present value. Before we solve either part A or B, let me go ahead and start to show you some, some notation and terminology that we will be using. So we're going to think a little abstractly here. We're going to think about, first of all, a net cash flow vector. Now, in physics classes, vectors are typically thought of geometrically as arrows, but in other math classes, if you're thinking about vectors, all you have to do is think about them as ordered pairs if they have 2 numbers involved, 2 variables, ordered triples if they have 3. In general, ordered n tuples with n quantities in them. Here actually, since we're going to start at 0, we're going to have n plus 1 numbers here that could be positive or negative. It's a net cash flow vector. Notationally, in books, you typically see these written with boldface. I could just call it C. It's not a real big deal if I just call it C. But I do like to emphasize that it's a vector. Now, some people put like a line under the vector symbol. I like putting a little half arrow. That does relate back to physics. You'll see sometimes physicists put half arrows, sometimes pointing this way, sometimes pointing the other way. I like pointing it that way. So this is just an ordered n tuple of numbers. It's net cash flow, so some of these could be positive and some negative. All right. I is not going to represent in the setup here the internal rate of return, the yield rate, though we could ultimately solve for I in a certain situation and it will be the IRR. But in general, I'm just going to call this an interest preference rate. I'll talk more about how to interpret the meaning of that in a bit here. You'll also see it called the cost of capital for reasons I will not get into in this video. Although I will mention capital in the video later on. And then we also have, for the given cash flow vector and the given interest preference rate, a net present value. NPV, which is really something we've been thinking about a lot. It's really just the present value of this cash flow, of this transaction, at the given interest preference rate, based on the corresponding discount factor, V being 1 over 1 plus I, as usual. Before I write down the general formula for it, I want to remark that notationally speaking, you're going to see this written in different ways. Sometimes you might see it written as, say, P of V. In fact, I did that in the last video. Sometimes you might see it written as P of I. So thinking of it as a function either of the interest preference rate or the corresponding discount factor preference rate, if you will. Though if you also want to emphasize what the cash flow vector is, you might put the vector in as a subscript like this. Okay? And you'll see that kind of thing, for example, in Kellison's book. And in fact, in Broverman's book later on, although in chapter 5 of Broverman's book, you'll see the role of the C and I switched around. You'll see them written like this. So this would be Broverman in chapter 5. Though later, again, for example, in chapter 7, you will see Broverman write it in one of these ways. Don't make too big a deal out of it, which way it's written. The way it's written kind of depends on what your goal is. You might write it in one of these two ways if you want to conceptualize the problem in such a way that C is fixed and either I or V is a variable. And I actually will do that here, though I'm going to use this notation. You would be more prone to use this notation in general if you want to think of I as fixed and let C be a variable. So you'd be, for a given interest preference rate, a given fixed value of I, you'd be comparing different transactions. But since we're comparing two transactions for different values of I, really both are variables. So, I'll go ahead and use this because that's what Broverman's using in chapter 5. But I think the main thing is just don't worry about it. Okay, it's not a big deal which notation you're using as long as you understand what's going on. No matter what notation you use, this is going to be the sum of the present values of all the cash flows. You could use sigma, summation notation here. Say k goes from 0 to n. The most common way to write this is as C sub k times V to the k power. Though, of course, that would be the same as the summation k goes from 0 to n, C sub k times 1 plus I to the negative k power, since V is 1 over 1 plus I, which is the same as 1 plus I to the negative 1. Okay, so that's the formula for it. All right, let's go ahead and write down this expression for both of these two transactions. Let me go ahead and give vector names to these transactions. This first set of 4 numbers with the A, I'll go ahead and call vector CA. Should I make the A a subscript or a superscript? It really doesn't matter. I'll go ahead and make it a subscript. Here we're making a superscript so that the subscripts can be the numbers 0, 1, 2, and 3. I could have made it a superscript. It's not really a big deal. And here it's C sub B. Okay, so I could write P sub I of CA. I'm going to write it like this. I'm going to use V's, which is a little funny because you don't see any V over here. But go ahead and do it that way based on these numbers that you see. So C0 is negative 5 times V to the 0, which is 1. We're not discounting that at all. That's already at time 0. 3.72 is at time 1. That needs to get discounted back by 1 period, multiplied by V. 0 at time 2. Add 0 times V squared. You don't have to write it. And then 4 at time 3. So we have a plus 4V cubed. And then P sub I of CB. Look at the second transaction there. Negative 5 plus 3V plus 1.7V squared. That's at time 2. Plus 3V cubed. All right, now before I go ahead and use the calculator to find the IRR, I want to mention briefly, and it's something you should look up. This is something that should be mentioned to actuaries at least once. There's something called Descartes' rule of signs that gives you a way to figure out the possible numbers of positive real roots and negative real roots, though we'll only focus on the positive ones. Look at each of these polynomials. There's only one change in sign as you go along the polynomial from lowest power to highest power, or vice versa, from highest power to lowest power. This initial change in sign from negative to positive with these coefficients here. In both cases, there's only one of those. What that means is there's actually guaranteed then to be one real root. And for V, it's only financially meaningful if it's positive. I meant to say only one positive real root. There's guaranteed to be only one positive real root. And again, for V, the discount factor, it's only financially meaningful if it's positive. So that's good. We only have one change in sign. We are guaranteed a unique positive real root for V. And that's going to correspond to a unique IRR for I. Okay? So let's go ahead now. Descartes' rule of signs is more general than that. If you have more than one sign change, then different numbers of positive real roots can happen. I don't want to go into the details. I would encourage you to look it up. Let's go ahead and find the IRRs now, just with the calculator. So let's look first at transaction A. Go into your cash flow worksheet. -5 is at time 0. Enter that. Positive 3.72 is at time 1. Enter that. Keep the frequencies at 1. 0 is at time 2. That must be entered. And then 4 is at time 3. Now you press IRR, CPT for compute. And for transaction A, it's given as a percent. The IRR is about 25.33%. And if we want 6 decimal places with the I, not as a percent, but as a decimal without a percent sign, you're going to get 0.253304. Okay, on to transaction B. Because I could have kept the -5 the same at time 0. Enter that. 3 at time 1. Enter that. 1.7 at time 2. And 3 at time 3. IRR CPT. We get an IRR that's almost the same as the first one, a little bit smaller, 0.25328. Okay, so transaction A has a slightly higher internal rate of return than transaction B. And that answers part A. So now we're on to part B. We really want to compare these as functions of V now in part B. In part A, we're just trying to find the I that makes them 0. In part B, we want to figure out what values of V, and therefore what values of I, make one bigger than the other, okay, for given interest preference rates. All right, let's focus on, okay, before I go into that, the details of that, what is an interest preference rate? Well, when you make investments, you can make investments certainly in stocks and bonds or other investment vehicles, but you also can make investments in capital, in buildings, in equipment, in people, and those investments can be thought of as giving you a return in higher profits, for example. It gets a little bit more complicated to deal with, though, because you always have to think about taxes, and you have to think about depreciation of equipment, for example. So it gets a little complicated that way. But when you invest in those things, you can think in terms of investment and return on those things. And maybe you need to invest in such things. Maybe you want your company to grow. You need to invest in new equipment or new buildings if you're going to grow as a company to make higher profits. So instead of investing in stocks and bonds, you decide to invest in capital. It's a decision you can make. And when you're thinking about these net present values, how do you decide in the preference rate to think about? I guess I would say think of it in terms of what, say you're imagining investing in bonds and getting a certain kind of return, a certain kind of yield. Think of that as your interest preference rate. That's something available to you. And now you want to invest in capital, and so you want to think about your net present value for cash flows generated by investing in capital at the same interest rate, the same yield rate that you can get with bonds. And maybe the net present value is even positive instead of zero, for example. And that would be good because, so compared to that investment into that bond, you're going to get more return. So you think about the values, the net present values, at those interest preference rates for which you could get that kind of yield on bonds, as an example of one way to think about it. All right, but now we're in part B, we are ultimately going to think about I as a variable. I'll still use this notation. Let's focus just on this part. Where is transaction B preferable to transaction A? And then the flip side will be the answer to the other one. So what we need to do is we need to think about when is P sub I of CB bigger than P sub I of CA? Essentially solve this inequality. Go ahead and replace these expressions by these two expressions. That would be equivalent to negative 5 plus 3v plus 1.7v squared. Looking at this one here, plus 3v cubed being greater than negative 5 plus 3.72v plus 4v cubed. And this can be solved for v more simply than you might imagine looking at it initially. Since it's a cubic, you might think it would be difficult. For one thing, the negative 5's cancel. Add 5 to both sides. Let me subtract, let's sort of switch the sides around here. I'm going to subtract 3v cubed from both sides, and after switching the order of things around, I'd have then a v cubed on this side. I'm going to get a less than because I'm switching things around. Less than 0, in fact. So I subtracted 3v cubed from both sides. I'm getting everything over here before I do the switching around. I'm going to subtract, let's see, 1.7v squared from both sides. So I'll get a minus 1.7v squared. And I'll subtract 3v from both sides to cancel over there and get a 0.72v here, but then again, I'm putting it on the left side now, like that. You can factor out a v. That's one thing that makes that nice because we canceled the constant terms. So if I can figure out where this is true, I'll be done. And I'm really after positive values of v here, financially meaningful values of v. This thing is a function of v. Its graph is the graph of a cubic. It's got a positive leading coefficient. 0 is one of its roots, and I'm hoping that its other roots are positive. It's probably going to look something like this. That's what I'm hoping, at least. Okay, and so the values of v that make this negative are going to be in here. These are the values of v where this is true. That's what I'm after, is an interval of values of v. And then that'll correspond to an interval of values of I, evidently I between 0.1111 and 0.25. You could use the quadratic formula to figure out when this is 0, and that should be helpful in factoring it then. V squared minus 1.7, oops, this is not a square here, sorry. minus 1.7v plus 0.72 equals 0. When does that happen? It's going to happen when v is 1.7 plus or minus. Square root of 1.7 squared is 2.89 minus 4 times 1 times 0.72 is minus 2.88, all divided by 2. Excuse me, I have to log into my computer here because it went to sleep on me. This is 0.01 inside there, then the square root of that is 0.1. This is going to be 1.7 plus or minus 0.1 over 2. 1.6 over 2 is 0.8, and 1.8 over 2 is 0.9. So when v, this allows us to factor this further as v times v minus 0.8 times v minus 0.9. This will be less than 0 for positive v when v is between 0.8 and 0.9. Now convert that to I. V is 1 over 1 plus I, so I is 1 over v minus 1. Convert that back to I. So for example, and 0.8 is, that's 4/5. So convert that back to I. We're going to do 5/4 minus 1. 0.9 is 9/10. Convert that back to I. That's going to be 10/9 minus 1. So I has to be between 1/4 and, oops, and the direction of the inequality has to switch around too. Sorry. Mistakes. And 1/9. In other words, between 0.1 repeating and 0.25, just like was set up here in approximate form, 11.11% and 25%. Okay? And on the flip side, A is going to be preferable to B when I is less than 0.111 repeating or bigger than 0.25. Okay, so we have finished the problem. Pretty important ideas in here. May have been new to you, maybe something you've struggled with. I hope this clarified some things. Sorry again for my mistakes. We'll continue doing a lot more examples in the videos to come.